Bueno, buenos días, ingeniero Alejandro. Buenos días, participantes al segundo día del primer Congreso Internacional de Ingeniería Geotécnica GeoUPC. Les doy la bienvenida al segundo día. Espero que también sea de su agrado, tal igual que el segundo día. Bueno, soy Julio Herrera, soy codirector del área de Relaciones Públicas y en esta ocasión me tocó ser el moderador de la exposición del ingeniero Alejandro. Bueno, hablando un poco más de la estructura que va a tener la exposición, es que primero presentaremos el equipo de GeoUPC, luego hablaremos un poco de la vida del ingeniero Alejandro Martínez, luego estará su exposición y luego tendremos una sección de preguntas del público asistente. Bueno, GeoUPC, somos un equipo conformado por alumnos de la carrera de Ingeniería Civil de la Universidad Peruana de Ciencias Aplicadas, UPC, y tenemos como razón de ser nuestra formación como profesionales en el ámbito de la geotecnia. Y conociendo al exponente, se trata del tópico de cimentaciones especiales con el tema específico Behavior of Bio-Inspired Piles, que es un tema sumamente interesante en lo personal. Bueno, y hablando del ingeniero Alejandro Martínez, es licenciado en la Universidad de Texas, Austin, Estados Unidos, en el 2010, máster y doctorado en Georgia Tech, Estados Unidos, en el 2012 y 2015 respectivamente, profesor asociado en la Universidad California Davis, Estados Unidos. Su investigación tiene como objetivo avanzar en la comprensión del comportamiento del suelo y las interacciones suelo-inclusión involucradas en la ingeniería geotécnica, así como la excavación y la locomoción. Además, emplea una combinación de laboratorio experimental, modelización por centrifugación y técnicas numéricas. Sus intereses incluyen en la geotécnica bioinspirada, las interacciones suelo-estructuras, los efectos del tejido en el comportamiento del suelo y la liquefacción estática de los suelos. En el 2019 coorganizó y codirigió el primer taller internacional de geotécnica bioinspirada. En el 2020 recibió el premio NSF Carrer y en el 2022 recibió un premio AC Arthur Casagrande Carrer de Development. Bueno, sin quitarle más tiempo al ingeniero, empezamos con su exposición.
Muchas gracias por la oportunidad de presentar hoy sobre nuestra inspiración, nuestra investigación en Bio-Inspired Piles. Yo soy originario de México, pero toda mi formación profesional ha sido en Estados Unidos, entonces la presentación la voy a hacer en inglés. Y bueno, entonces aquí vamos. The research today, I do want to acknowledge it's based on the research performed by many students, as indicated down here. And today I want to introduce the work we have been doing on bio-inspired piles and how we have gone from the fundamentals, understanding how things work, to implementing or starting to implement these piles in the field. This is an outline of my presentation. I'll start with the motivation and background. Then I will show the skin friction and how that has directionality. And what I mean by directionality is dependence on direction, mobilizing different skin friction in different directions. And so I'll show some results on how the friction changes, the dilatancy changes, and then on the cyclic behavior. Then I'm going to show an implementation on piles using a geotechnical centrifuge here at UC Davis. Then I'm going to briefly introduce some field tests that we performed this past summer, and then I'll close up with conclusions. So motivation and background. At the heart of bioinspiration is sustainability and mitigating the environmental impacts of construction. I think we all know why this is important, and that's essentially because construction practices use materials and energy at rates that really cannot be sustained in the future, as shown in this plot in terms of the material usage per year, showing that construction materials are responsible for a very large portion of that material use. 75% of raw material use, 55% of off-road fuel use. And so if in civil engineering we can improve and use less material and make our processes more efficient, we can actually have a great impact in sustainability and environmental impacts. And going down to by inspiration and why we may be interested in this. Well, we can be interested in this because there's a lot of parallels between the engineered and the natural systems. In civil engineering, we need to build tunnels. We need to build tall and slender structures that are subjected to wind loads, for example. We need to deliver sensors to monitor the ground conditions, build tall structures, and excavate. And that is really not that important. That's not that different than what many animals and plants do. For example, snakes move on loose ground. Trees are really tall and slender structures, and the roots are their foundations. And there's a range of animals that are really experts in burrowing and digging, from clams to earthworms to moles. So there's many things we can learn from these. At the heart of bioinspiration is this idea that some of the biological strategies, that's how an animal or a plant accomplishes something, they have been shown to be more efficient than human technology. In terms of excavation, this is research that shows that the efficiency in terms of joule per unit volume of a tunnel boring machine, as the one shown here, is a lot lower. We need to use a lot more energy, 2 to 3 orders of magnitude more than ants use to excavate their tunnels. And so clearly ants are doing something that's more efficient, and we can learn something from ants. And then in terms of anchorage, if we look at the root systems of trees and we calculate efficiencies in terms of capacity per unit volume of the root system or capacity per mass, we see that these efficiencies are about 10 times higher than conventional micropile systems that we use in geotechnical engineering. And so there's also something we can learn from the anchorage. However, one important thing here is how do we translate these strategies to geotechnical engineering? We may think ants are very small and the tunnels are just a few grains wide. And so how do we translate? And so this is where we really need to do a couple of checks, very important checks. The first one is if the biological strategy translates to the spatial and temporal scales of engineering applications. What that means is these organisms live in very shallow conditions, typically less than 1 meter, where the stresses are very low, 1 to 10 kPa. How does that translate to much deeper locations where the effective stresses can be significantly higher? We need to make sure that translates. And the other one is very fundamental. And the other one is that the behavior of soils depends on the soil type, but also it depends on the magnitude of the forces between the particles. So here I show these are analytical relationships between 2 spherical particles, showing the interparticle force in the y-axis and the diameter of the particles on the x-axis. And I want to highlight this dashed gray line. These are the effective stress forces or skeletal forces. So when the stress is really high, 1 megapascal, then the skeletal forces really drive the behavior. They're the greatest magnitude, and so they drive the behavior. But if we have low skeletal forces, when we're in shallow conditions, let's say 1 kPa, then it could be the capillary forces that control. It could be the drag forces. It could even be the electrical forces. And so, again, the mechanism could change between shallow locations and deep locations. So now moving on. Now we know why bioinspiration can help, but we know that there are some challenges translating the biological strategies. So now starting to look at the skin friction at soil structure interfaces. We look at soil structure interfaces because most of the load that's transferred between structures and soils takes place at those interfaces. So all this figure, I really like it from Hayward Baker, who's now part of Keller. But these figures show all the planes of contact between the soil and the structures that we build. All of those planes of contact are where the load is transferred. Examples are many: deep foundations, soil nails, tiebacks, tunnels, and many others. Particularly, what we're trying to address is this issue that many of our geotechnical elements are subjected to loads in opposite directions during their installation and service life. And this creates what I like to call a dilemma, because we want really high skin friction, because that gives us a high capacity, right? High skin friction, for example, for a pile will translate to a large capacity. But at the same time, if the pile is driven, high skin friction creates challenges for installation. So at the same time, we also want a small skin friction so that we can install foundations easily, for example. I have 3 examples here. A pile, we install it, the skin friction is opposing that installation, but if we load it in tension, then the skin friction direction flips, and now it helps us. For suction caissons, it's the same situation. We install them, the skin friction resists that installation, but when we actually load them, then they're providing the capacity. And also piles in settling ground where we may have down drag also experience loads in different directions. And so this is what we're trying to address. How do we optimize this process? This, as you can imagine, are for more specialty types of foundations that are loaded either in tension or in both directions. And just for reference, usually the tensile skin friction divided by the compressive skin friction of a pile is in the range of 0.4 to 0.8. So usually the tensile skin friction is smaller, maybe about half, maybe 75% is a typical value. So now we looked at biology. We did a search. We collaborated with some biologists to find the right analog, the right source of inspiration. We looked at gecko feet, at shark skin, and beetle feet. And all of those are very anisotropic, but all of those, as you can see, rely on bending. So these little hair structures and these little scales bend quite a bit. We also looked at grass leaves, and grass leaves are very, very anisotropic. And here we can see why. They have these spikes that also bend and latch on. We ended up looking at snakeskin, and that's the solution we chose. And we chose it because these structures are pretty rigid compared to the other ones. And so rigid more like construction materials, like steel and concrete. So we're going to be looking at the ventral scales. Those are the scales on the belly of the snake, these ones over here. This is a 3D scan of snake skin. And I can take a cross-section from point A to A prime, and I get this profile. And we can see that the profile is quite anisotropic or asymmetric, with one mild slope side and one sharp one. And here I need to introduce 2 directions. The caudal direction would be if I move this skin to the left on the screen here, then a particle here would be sliding on this milder slope. And this caudal direction typically mobilizes smaller frictional resistance. And there's the opposite direction. The cranial direction is if I was to move this skin to the right, you can imagine the particles will get stuck and encounter this sharp edge. And this cranial shearing mobilizes higher frictional resistances. So I'm going to have this key up here, this schematic, just to remind what cranial is, would be moving this skin to the right. Caudal would be moving this skin to the left. Okay, so how we did our bio-inspiration. We, sorry, give me a second. All right, perfect. We first obtained 60 snake specimens from the Museum of Vertebrate Zoology at UC Berkeley. So we actually brought snakes to our laboratory. They were preserved, so they were dead, But that allowed us to actually look at the snakes and look at their skin. And we collaborated with a colleague, Professor Brian Todd, who's a biologist. We scanned all of their skin to generate 3D scans, 3D schematics. Then we idealized, scaled, and 3D printed these surfaces that are representative of snake skin. Then we performed interface shear testing. Today I'm going to focus on sand, but we have also performed tests on clay. Then we performed centrifuge pilot tests, as I'll talk about today. And then finally, we moved to the field. And instead of looking at piles in the field, we looked at soil nails. And so we installed the soil nails in 2 sites. One's a fine-grained soil site and one's a sandy site. And so I'll also talk about those. Starting with our laboratory testing, we use the Ciiggupc interface shear tests. We have tested different sands at different densities, but today I will be talking about dense Ottawa 2030 sand. And so this is a schematic. This is the Ciiggupc, and we have a sand specimen in there, and then we have our bio-inspired surface over here. The bio-inspired surface looks like this, and it's characterized by the length of the asperities, L, and height of the asperities, H. So most of the results today are for a particular surface with height of 0.3 millimeters and a length of 12, although I will show some results where that is different. So just to show the response, first I'm going to show the shearing response of a rough surface. This is like rough concrete, and smooth profile. This is polished steel. And so this is what the results look like. This is the stress ratio. This is just a measure of the interface strength as a function of the horizontal displacement. So we move in one direction with the rough one. That's the solid black. We get a large strength. And then we stop, we move in the opposite direction, and we get also a large strength. And we can see the strength in either direction is very close to each other. With the smooth, as we would expect, the interface strength is a lot lower because smoother interfaces typically do not interlock with the particles. And so the strength is smaller in one direction and then in the opposite. Now we're going to bring our bio-inspired surface. And so that's this one. We are first moving in the cranial direction. And so the strength is high, very similar to the rough. Then we stop and we start moving in the opposite direction. And so then the strength in that other direction is low. It's much smaller, similar to the smooth. And so this is this concept of frictional directionality, that one single surface on the same test can mobilize a large strength if it's moving in the cranial direction, or a low strength if it's moving in the caudal direction. This is the opposite test. We do caudal shearing first, the strength is lower, and then cranial and the strength is higher. These results are very similar. They're just showing now the shear stress versus horizontal displacement. The cranial shearing mobilizes a large stress, similar to the rough surface. And the caudal shearing mobilizes low strength, similar to the smooth. And so this is very similar. What I want to highlight is now what happens with the volume changes, with the dilatancy. As we would expect, a very rough surface has a lot of interlocking with the particles. So it dilates a lot. That's this response we see here. And the cranial test dilated quite a bit, very similar to the rough. And so that goes hand in hand with the similar strength that we observed. For the caudal shearing, we see a little bit of dilation, but not nearly as much. And so this behavior is more representative of a smooth surface. So we can perform a series of tests. Here we perform the test at different effective stresses to quantify the interface friction angles. So these are the failure envelopes. And what you can see is that the difference in the friction angle is about a factor of 2. In the cranial direction, we have 29 degrees. In the caudal direction, we have about 15 degrees. What's interesting is that it it doesn't matter how we do the test. We can do cranial first and caudal second, or caudal first and cranial second, and we mobilize the same failure envelopes. And so our space in terms of failure envelopes looks like this. If we test in the cranial direction first, we have this steeper failure envelope on one side, on the cranial side, than on the caudal side. But if we were to shear on the caudal side first, then we have this smaller friction angle on the caudal side than on the cranial side. I just wanted to show, and by the way, these are all for this one surface, height of 0.3, length of 12. So I wanted to show what happens when we change those two dimensions. We can change the height and we can change the length. As you can imagine, this is a problem because we can have an infinite number of combinations between heights and lengths. And so we were looking for a parameter that unified both. And a simple ratio of the length to the height seemed to capture the trends. And these are the trends. This is the peak strength as a function of that scale geometry ratio. And we see, first of all, that cranial shearing always mobilizes a greater strength, but that then with the scale geometry ratio, the trend looks like this. It goes from high to low, as shown here. And also in terms of the dilation angle, we get greater dilation in the cranial side, and that dilation angle drops with the scale geometry ratio. Can I just get confirmation that you still see my slides?
No, no se puede ver. Creo que dejó de compartir su presentación.
Ok. Ahora, ¿sí se ve?
Ahora sí se puede. Ahora sí se puede.
Ok.
Sí, ahora.
Bueno. Okay. So we wanted to get a better understanding for what's happening. So we did particle image velocimetry, PIV. We use the software GeoPIV that essentially what it does is it tracks images. We take many images during a test and we track patches of the texture. And then it uses cross correlation to calculate the displacements and the strains in the specimen. So this is an image of our specimen. You see we had to dye the sand in blue. And that's just so that we could get more contrast, and that improved our analysis. So this is the PIV analysis. Again, these are all experiments, but with the image processing, we can obtain the deformations. And so this is deformation distribution, x coordinate, y coordinate. Here we have a surface at the bottom, and we're moving that surface to the right. And that surface has two scales, 1, 2. And so on the cranial side, we see something interesting. Ahead of each scale, we see this zone where the shear strains localize. So we have these two localization zones ahead of each asperity. On the caudal side, that's the side that mobilizes smaller strength. We don't really see that trend quite as much. And so this difference in the deformation mechanisms is what drives the difference in strength. We can also look at the volumetric strains, and we see dilation ahead of the asperity in blue, and contraction behind of the asperity in both. We, again, don't quite see that on the caudal side. And so it's that ability to interlock and deform the material more that's providing the greater strength. The next thing we wanted to do is to link the dilatancy and the state of stresses. This is very similar in a pile, for example, for deep foundations. If we have a pile, this is a pile looking at it from the top. As we start loading it, the radial stresses around the pile may change. They may increase or they may decrease. And so to do that, we have this constant stiffness model. that represents the soil in the far field using elastic springs. And these elastic springs have a stiffness K that's dependent on the soil stiffness G and the diameter of the pile. If we now look at a side view, that's our pile. We have our stiffness K, and then we have a normal stress that may change. And this delta is the dilatancy at the interface. If the soil is dilative, it'll move to the left. If it's contractive, it'll move to the right. And that can be represented with an element of soil, again, with a spring that couples the dilatancy with the current normal effective stress. So this is our model. In a laboratory test, we just flip it on its side. There's the soil element, stiffness, normal stress, and dilatancy. And the normal stress is linked to the dilatancy by this equation, where essentially we have the initial normal effective stress, and then we add K times the dilatancy. And so this is the spring constant stiffness term. So we perform these tests. These tests are called constant normal stiffness tests. And so what I'm showing here is a shear stress as a function of the displacement. And now we see that we start shearing in the cranial direction, and that strength goes very high, and that's greater than the caudal direction. We already saw this type of results where we have greater dilatancy in the cranial than in the caudal. But what's interesting now is plotting the changes in the normal stress. And now, because they're coupled using this equation, then the stresses in the cranial direction increase significantly more than in the caudal direction. And so it's not only the friction angle that leads to these differences, it's also how the normal stress changes. And so we know that the friction angle in the cranial direction is greater, the dilatancy in the cranial direction is also greater, and that leads to greater increase also in the cranial direction. And we have verified the strands for different sand types and different stiffness values. So now we can do a little bit of cyclic testing, and this is interesting. First, this is our space, right? The two failure envelopes, caudal first, cranial second. The first thing we're going to do is do cycles, but that are symmetric. So the average is 0. We go up to a given value, and then we go down to a given value, up and down, up and down. And this is the amplitude, 0.35 of the capacity. So let's look at those results. This is what it looks like. We start going in the caudal direction and then cranial, caudal, cranial, caudal, cranial, about 30 times until we get a failure. This is a pull-out failure on the caudal side. We can look at how the volume changes are accumulating. We're contracting, contracting. With each cycle, we contract a little bit until we get this pull-out failure. And this is the stress path in the shear stress, effective stress space. We start cycling, and as we would expect, in a way, this is similar to cyclic mobility. We cycle, cycle, cycle. The effective stresses are decreasing until we hit the failure envelope, and that's when we get this failure in the caudal direction. And that's because the friction angle is smaller. We can do the opposite test, where we do cranial, caudal, cranial, caudal. So I just reversed the sequence. The behavior here looks very similar. We're dropping, 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 contracting until we get this failure. And the stress path also looks very similar. We're cycling, cycling, cycling until we hit the failure envelope in the caudal side, and that's where we get the pullout. We can start to do more interesting things, like we can introduce a bias. This would be a static stress that's on the cranial side always. And we tested different values. Here I'll show you results for 10% bias and 15% bias. And this is what the results look like. We go caudal, cranial, caudal, cranial. Now you see that the magnitude in the cranial side is about it's greater than in the caudal side. And so we start cycling, we have a greater accumulation of deformations, we see the contraction, and then we see that at the end we have a failure on the caudal side because we hit that failure envelope first. But it was very close. It almost failed in the cranial side. This is the opposite. This is the other test with a bias of 15%. We do caudal, cranial, but now we see that the behavior is really accumulating deformations on the cranial side until we get a failure on the cranial side because we reach that failure envelope first. And so if we introduce a bias that's large enough, we can make the surface fail on the cranial side. However, if the cycling is symmetric around 0, then it'll always fail on the caudal side. So some conclusions here. Shearing in the cranial direction mobilized a greater interface strength. And so in the cranial direction, the friction angle was about twice as in the caudal direction for this particular surface. A larger asperity height and a larger length influenced the behavior. Greater height led to greater strength because it increased the interlocking. And a smaller length led to a greater strength because shorter asperities means more asperities. So again, we could interlock more. Cranial shearing led to greater amount of soil deformations, as we saw in our PIV analysis. And cranial shearing also led to greater increases in normal stresses. We saw that under symmetric load, the failure always took place in the caudal direction. That's because of the difference in the friction angles. And a load bias of 15% led to failure in the cranial side. So now I want to move into the discussion on the piles and how this translates to the behavior of piles. To do this, we used our centrifuge at UC Davis. We have a centrifuge that has a 9-meter radius, and you can see it here. It's quite large. You can see the people there for scale. For those of you that are not familiar with centrifuge modeling, essentially what we do is we start spinning the beam. So this starts spinning around the room. This hinge rotates, and so the bucket, that's where the experiment is. And so this will swing out, and then we will have a centrifugal acceleration pushing out. And here you can see an image of our pile with some of the instrumentation. We perform our test at 30 G, so 30 times of Earth's gravity, again by spinning. We performed the test on dry, poorly graded sand at a relative density of 65%. We installed the pile in flight by quasi-static pushing. We perform monotonic and cyclic loading, although today I'm only going to discuss monotonic. And all of the results here are provided in prototype scale. Let me just introduce centrifuge testing a little bit. This is just an example. We may have a prototype. This is like a deposit of soil, right? This is like a sand site, for example. And so we can calculate the distribution of stresses with depth using this equation. We all know it's density times gravity times depth, right? And the overall depth of this deposit is LP. What I can do is I can subject a model, let's say to a gravity of 2G. So I increase the gravity to twice of Earth's gravity. So the G scaling factor is 2. What will happen is that to get the same magnitude of stresses at any depth, I will have density. It doesn't scale with G. Gravity is scaled by 2, but then the depth needs to be divided by 2, and this 2 is canceled with this 2, and I end up with the same stress. And so all of that results in the depth of my centrifuge model being half, because the scaling factor is 2. If the scaling factor is 10, then it would be a tenth. If the scaling factor is 100, it would be 100. And so centrifuge modeling allows us to produce a realistic stress and stress distribution in controlled experiments with well-defined boundary conditions and material properties. So it's a way of upscaling, but maintaining well-characterized tests as we do in the laboratory. So this is what our pilots look like. This is the pilots that we performed the load test on. In prototype at 30 G, they had a length of 10.5 meters and a diameter of 0.6. They're instrumented with internal strain gauges, so you can see the cables coming out. The strain gauges are on the inside. We have 5 different textures. This one is one of the bio-inspired ones. We installed it in the cranial direction, and so you can imagine the particles encountering the sharp edge. We have the caudally installed piles, and you can imagine this one's the particles will slide as we're installing the pile. This one is a rough pile, just as a reference, and we also have a smooth pile. So let me show some results. These are load distributions. So what I'm going to show here are forces as a function of depth or length along the pile. So these 2 results are what we would expect. For the rough pile, we mobilize large forces, and those forces are shed quickly to reach a base capacity here of about 6 meganewtons. And these forces are a lot bigger than for the smooth pile. And that is because the skin friction is a lot greater. This is what we would expect. And by the way, this is color-coded. So now the pile that looks like this, cranially installed, so it's harder to install in dark green, mobilizes loads very similar to the rough pile. So the distribution looks like that. And then the 2 other piles that are caudally installed, they have a different height, 0.3 and then 0.7. Even though this one has a taller asperity, it's easier to install. We see the forces are similar to the smooth one. Okay, so we see the effect of the texture and the orientation. Now let's see what happens when we do a tension test, a pull-out test. The rough pile mobilizes a large capacity, as we would expect, significantly greater than the smooth pile. So shown here. The dark green pile that was difficult to install, like the rough, is now easier to pull. It mobilizes a smaller capacity. And that's because of the directionality. It's easier to pull this pile than it is to push it. Now, the other 2 piles, the ones that mobilize the small installation forces, now mobilize the greatest tensile capacities. And that's because of the interlocking. You can imagine the particles interlock with the asperities in the cranial direction, and that leads to this large strength. I'm going to take a closer look at these 3 piles to highlight some of the trends. These are local stresses. So these are skin friction as a function of depth. Solid symbols are for compression. Empty symbols are for tension. And so for the rough pile, the one in red, if I take the ratio of these distributions, I get about 0.4. And so this is similar to what we would expect in the field. The pile that we install cranially and pull caudally mobilizes significantly greater installation forces. And so that ratio is about 0.2, very low. But this part is really interesting for the pile that we pull cranially. Now the tensile capacity is bigger than the compressive capacity, and that ratio is about 1.4. This means that the tensile capacity of this pile is 40% bigger than its compressive strength, which is a very unique behavior. We can take a look at load transfer relationships, TZ type of relationships, at different depths. So 3 is 3 meters under the ground surface, 6.8 is the deeper one. So we see for the rough, they go like that. For the cranially installed caudally pulled, this is all in pull-out, so the shear stresses are smaller, and they're actually greatest for the cranially pulled pile, the purple one. And so here again, we see both mechanisms taking place. we have the difference in the friction angle. But another part that's probably more important, particularly for piles, is the fact that the effective stress is greater on the cranial side than on the caudal side. And so some takeaways from here. The skin friction magnitude and its distribution with depth depended on the direction of loading relative to the orientation of the bi-inspired texture. In other words, the skin friction in the cranial direction was always greater than in the caudal during installation and pullout. While we know that the friction angles are different, they're greater in the cranial direction, the skin friction difference depends also on the normal stresses acting on the pile surface and how they change based on the bi-inspired texture. I mentioned we performed cyclic tests. I didn't show those today, but we have a paper that we're getting ready to submit on that, and also we have plans for a field deployment of piles. So now moving on to the last part of my presentation, field tests on snakeskin inspired soil nails. We performed these tests this summer, actually, in Davis, right when it was the hottest. I think it was about 43, 44 degrees Celsius for a couple of these field testing days. We performed tests on 2 sites, one on a poorly graded site, that's this one, and one on a silty clay, that's this one. We now are focusing not on piles, but on soil nails. And we only installed those vertically just for simplicity. We know that soil nails are really close to horizontal. We didn't have the equipment to do that, and so we just installed them vertically and then pulled on them. These soil nails wouldn't be grouted, as many of them are. They're more similar to what they call the launched or driven soil nails. And so this is our drill rig. This is what we use to push our soil nails, and then we use the same drill rig to then test them in tension. And then we did tests on 8 different surfaces with different lengths and different heights. And this shows a picture of sections of all of these soil nails. These ones have a small height, 0.0 millimeters, and a short length. Here, these ones, for example, have a very large height, 4 millimeters, and a length of 12. And we also tested some rebar, just because rebar is very rough. And so our rebar was a reference rough soil nail. So let me show you some of the results. We're really happy when we saw these results, because the results agreed with the laboratory and the centrifuge tests. Here I'm showing the results in terms of the stress ratio. That's the average skin friction divided by the vertical effective stress as a function of displacement. And so we see that when we have a greater height of those asperities, we mobilize a greater strength. And so we see that very high value, particularly for a height of 4 millimeters, really, really high value that then starts dropping. At 2 millimeters, we have less than half the capacity, and then that keeps dropping as we decrease the height. And interesting, the reference rough surface, so the rebar, was the lowest, significantly lower than all of the other ones. We can also look at the effect of the length. The effect of the length here shows for a fixed height that when we have many asperities, length of 12, we have a high strength peak, but then it softens quite a bit. If we increase the length, then the behavior is a lot more ductile. It keeps increasing, and it doesn't strain soften quite as much. So here we see the effect of both. And one interesting thing again is that the L/H ratio, this is the length divided by the height, unifies the trends. We get this parallel relationship if we plot the results in terms of the L/H. And so this appears to be a good parameter for the design of this of the texture. You can imagine one of the challenges in design with these textures is, again, that there's an infinite number of possibilities of combinations of lengths and heights, but this ratio seems to unify the trends quite nicely. So now I want to move to my closing thoughts. In terms of load transfer first, we tested these snakeskin inspired surfaces with asymmetric profiles. And they mobilized directional dependence in the strength, as shown in this figure, in the dilatancy, local soil deformations, shearing in the cranial side, mobilized significantly greater deformations, and also cyclic degradation and failure behavior. We performed a number of centrifuge pilot tests, and we saw greater total and local skin friction in the cranial direction, as shown, for example, in this image, showing that the tensile cranial capacity can be as high as 40% greater than in the compression side. We performed the field test on soil nails, and those agree with laboratory and centrifuge results. We're actively looking for collaboration opportunities with industry. We've really liked our implementation on the soil nails, and we would like to continue with that, but we also would like to do an implementation on a pile at full scale, half a meter of diameter, or something like that. And we've done other work that's not presented here. For example, in the interface shear behavior with clay soils, the behavior with surfaces with compliant asperities, cyclic behavior piles. And we've even were able to make a contribution to the biological literature by analyzing the 3D scans that I showed at the beginning. I have some other closing thoughts that are a little more broader in terms of bioinspiration, and that is that there are hundreds of biological strategies that address challenges that are analogous to those in geotechnical engineering. So bioinspiration is a very powerful tool. If we want to look for solutions for load transfer, soil penetration or excavation, slope stability, mass and thermal transport through porous media, optimization, many others, we can take a look at bioinspiration. There are some important steps. For example, familiarizing with the biology literature and collaborating with biologists. This is, in my view, very important, because when we start looking at an animal or a plant, that's really not our expertise as engineers. There's a whole range of complexities that we need to consider, and collaborating with biologists are the best ways to do that. And also the need to find questions that are of common interest, both to the engineering as well as to the biology science. And the research can focus on very fundamental things, like, for example, quantifying the relationships between snakeskin topology and habitat use. This is a very fundamental question. But we can also address very practical challenges, like, for example, developing new types of surfaces for foundations and soil reinforcement element to develop directionally dependent strength and failure behavior. This is where we're trying to head with our research. Just two more things I wanted to share with before I finish my presentation. One is that we had a workshop on bioinspired geotechnics, the first international workshop. This was in California in 2019. It was funded by the National Science Foundation of the United States. We had 60 attendees from academia. And so we brought people from geotechnical engineering, from material science, mechanical engineering, biology, physics. So we really brought a very interdisciplinary group of people. We also brought people from industry, people from the foundations industry, ground improvement, site characterization, geoenvironmental and monitoring. We had people from Contech, from Keller, from GeoComp attend and also give their perspectives. The results of this workshop are published in a paper in Geotechnique that you can see here. The title is Bio-Inspired Geotechnical Engineering, Principles, Current Work, Opportunities, and Challenges. And the other thing I wanted to bring to your attention is that we have a special issue in Acta Geotecnica right now. There's a call for papers. We have different topics that we're looking for contributions: organism geomaterial interactions, translation of biological strategies to geotechnical engineering, application of bio-inspired and nature-inspired solutions to geotechnical engineering. The deadline is December 31st. We've already received about 15 papers. And you can see the applications can be really anything: foundations, tunneling, site characterization, and so on. This is an effort that's being led by Julian Tao from Arizona State, as well as myself. And so if you have any related work, please feel free to reach out to me or to Julian Tao, and we can discuss this. So with that, I just want to acknowledge the hard work of all of the students in my group. Kyla Hora, who's close to graduating, Lin Huang, who's a PhD student, Sofia Palumba, who's an alumni, Damon Gwen, that's a PhD student, and Mandeep Bason, that's also a PhD student, as well as collaborators from around the world, as well as the funding agencies, the Center for Biomediated and Bio-Inspired Geotechnics, the Center for Geotechnical Modeling at UC Davis, as well as NSF through different grants. So with that, I'm happy to answer any questions if there are any, and I want to say thank you again for the invitation and for having me.
Sí, ingeniero, muchas gracias por su presentación. Agradecemos que comparta su conocimiento con ensayos, bueno, experiencias y todo eso. Tenemos unas preguntas muy interesantes que han hecho los asistentes al congreso de la exposición de hoy.
Okay.
La primera pregunta sería: ¿podría aplicarse el principio de la piel de serpiente a los elementos estructurales? Y en caso afirmativo, ¿cómo se aplicaría?
Es una muy buena pregunta. La verdad es que no lo he pensado mucho. No lo he pensado mucho. Para los elementos estructurales, me imagino que si algún elemento estructural disipa carga por fricción, entonces sí se podría usar. O por ejemplo, si se desea tener una acumulación de deformación hacia una dirección y no hacia la otra, yo creo que eso sería una buena aplicación. La verdad es que no soy un experto en ese tema, entonces no puedo dar ejemplos muy específicos, pero otras aplicaciones que hemos visto, por ejemplo, es para llantas de vehículos, para evitar que se pierda la tracción, por ejemplo. Entonces, si alguien en la audiencia tiene ideas, las podemos discutir.
Sí, mientras van pensando sus ideas, puedo decir la segunda pregunta, que es: ¿qué le inspiró a investigar y profundizar el tema de la geotecnia inspirada en la naturaleza?
Sí, claro, esto es un tema que combina, digamos, dos de mis hobbies o de mis intereses. Obviamente la geotecnia pues es mi pasión, es lo que hago, pero a mí siempre me ha llamado mucho la atención la biología y los animales y entender cómo pueden hacer cosas tan impresionantes. Entonces, en mi doctorado, como que, pues casi como un pasatiempo, empecé a leer artículos en biología, porque la verdad es que hay, por ejemplo, muchos biólogos que estudian cómo, por ejemplo, una serpiente se mueve sobre arena. Y ellos usan muchos conceptos de mecánica de suelos. Ellos usan failure envelopes, ángulos de fricción interna, todo esto. que aprenden de nosotros, de los ingenieros de suelos, ¿no? Entonces, ahí fue como empecé a hacer la conexión, en empezar a aprender sobre esto y empezar a hacer como una abstracción, que es, la abstracción es el proceso de entender cómo un animal o una planta hace algo, extraer el principio y después tratar de aplicarlo a una escala diferente, como sería una cimentación, un pilote o algo así.
Muchas gracias por la respuesta. Creo que podría inspirar a muchos de la audiencia a hacer diferentes investigaciones. Y ahora con la siguiente pregunta. ¿Cuál fue el mayor reto en su carrera profesional respecto a este tema?
Sí, esa es buena pregunta. Yo creo que eso ya va cambiando un poco, la verdad, pero un reto pues que se ha tenido pues desde el principio es que muchos ingenieros, sobre todo, pues digamos, con una formación un poco más tradicional, pueden tener como un escepticismo hacia este tipo de investigación, como que pensar, ¿por qué estamos estudiando serpientes? ¿Por qué estamos estudiando una lombriz? Como no creer que eso pudiera ayudar a mejorar nuestra profesión. Pero ya llevamos haciendo esta investigación casi 10 años y yo veo que la trayectoria va muy bien. Cada vez que hablo pues con gente de la industria o con investigadores, cada vez se nota que están más informados sobre esto y que hay más interés. Entonces yo creo que eso como convencer a la industria de intentar cosas nuevas ha sido pues un reto, pero al mismo tiempo eso ha sido parte pues lo interesante de este trabajo, de hacer la investigación a fondo, digamos, a una escala más fundamental y después pensar en verdad, en qué áreas de la industria se podría ayudar, cómo manufacturar, por ejemplo, estos elementos de cimentación y todo eso es otra parte que es súper interesante. Entonces, así como nosotros podemos aprender de la industria yo creo que puede aprender de nosotros también.
Ingeniero, como dice, algunas empresas se quedan con lo tradicional ya que piensan que si funciona no hay que cambiarlo. Pero bueno, tenemos otra pregunta de Maciel Padilla, que es, ¿cuáles pueden ser los inconvenientes de este tipo de estudio?
No estoy seguro en qué este tipo de estudio de investigación o será de estudio de...
Tipo de investigación.
Pues yo creo que las dificultades son... este es un tipo de investigación muy interdisciplinaria, ¿no? Entonces, tenemos que aprender sobre la biología, tenemos que colaborar con biólogos y la verdad es que esa es la parte más difícil, pero al mismo tiempo es la parte más interesante. Es la parte más difícil porque, por ejemplo, si yo quiero entender un organismo, pues muchas veces tengo que traer el organismo al laboratorio y los animales o las plantas, pues muchas veces no cooperan a hacer un experimento. Si queremos que el animal se mueva y el animal no se quiere mover, pues ese es un problema, ¿no? Entonces, eso pues puede ser un inconveniente, pero al mismo tiempo, ese tipo de interacciones y trabajar con gente de otros campos es donde podemos aprender más, donde podemos expandir las ideas que tenemos, las herramientas con las que analizamos los resultados, por ejemplo. Entonces, esa ha sido una experiencia que ha sido, pues ha sido un reto, pero al mismo tiempo ha sido de las experiencias más gratas que he tenido.
Ingeniero, tenemos otra pregunta de William Talavera, que es, quisiera saber si el clima, ¿qué impacto tiene el clima frente a su investigación y cómo afecta?
Sí, claro, en cuanto a... yo creo que la puedo responder de dos perspectivas. Una es de cómo el clima afecta a los animales. Y eso sí lo estudiamos con todos los scans que hicimos de 3D de las serpientes. Hicimos un análisis en colaboración con colegas de biología para entender si había relaciones entre el hábitat donde viven los animales, las serpientes, y el tipo de piel que tienen. Por ejemplo, la altura de las escamas o la rugosidad. Entonces hicimos un análisis y sí encontramos que, por ejemplo, las serpientes que viven en los árboles son las que tienen la piel más rugosa. Y las serpientes que escarban, subterráneas, son las que tienen la piel más lisa. Entonces, eso sí lo entendimos. Y en cuanto al comportamiento por ejemplo, estos pilotes en diferentes tipos de suelos no saturados o suelos saturados, la verdad es que también ha tenido una influencia importante, y eso lo vimos en los ensayos de campo que hicimos este verano, en el sitio, en el site, donde tenemos más arcillas. Es una arcilla muy disecada. El nivel freático está como a 30 metros debajo de la superficie, entonces la arcilla está muy disecada, entonces hay mucha sensitividad. Entonces la instalación del soil nail, pues digamos, puede dañar el material y eso afecta la capacidad que se tiene después en tensión.
Ok, ingeniero, tenemos una pregunta de un participante del Congreso, que es, ¿qué potencial tiene este tema contra el cambio climático? ¿Y se podría utilizar más materia viva como plantas en los muros para bajar la temperatura? Pero ¿qué otra cosa se podría realizar?
Sí, claro, digo, no específicamente, o no solo el tema de la piel de serpiente, pero todos los temas de bioinspiración, yo creo que pueden ayudar para el cambio climático, sobre todo desde un punto de vista de sostenibilidad. Y eso es porque todas las adaptaciones de animales y plantas, todas sus estrategias, son por definición muy eficientes, porque los animales y las plantas solo tienen una cantidad finita de energía y de materiales. Por ejemplo, un topo, el que está aquí en la pantalla, solo puede escarbar dependiendo de la comida que ha comido, ¿no? Él no puede traer otro tanque de gasolina y seguirlo haciendo. Asimismo, está limitado por los materiales que tiene, por las uñas que tiene, por los dientes que tiene. No puede usar materiales como metales o como rocas. Y nosotros sí podemos. Y esa habilidad que tenemos los humanos de usar más energía y de usar más materiales es la que nos ayuda a tener una capacidad superior para hacer muchas cosas, pero al mismo tiempo es lo que nos hace ser muy ineficientes en lo que hacemos. Muchas veces, en lugar de mejorar el proceso, simplemente usamos más energía, más gasolina, más diésel. Entonces, al entender lo que hacen los animales y las plantas, al entender sus estrategias y después adaptarlas, no copiarlas directamente, pero adaptarlas a la ingeniería geotécnica, podemos descubrir o podemos desarrollar nuevas tecnologías. Un ejemplo es, por ejemplo, las anclas o las cimentaciones inspiradas de las raíces de los árboles. Ahí la verdad es que el material no está cambiando mucho. Lo único que está cambiando es la geometría. En lugar de ser un elemento lineal, una columna que se hinca en el suelo, pues ya tiene una geometría en 3D que cambia cómo se transfiere la carga y puede hacer de estos sistemas de anclas 20, 30 veces más eficientes. Claro, hay obstáculos como cómo se construyen, cómo se instalan, que eso es lo que se tiene que desarrollar, se tiene que desarrollar la tecnología. Pero en cuanto al potencial, yo creo que es muy, muy grande.
Bueno, tenemos otra pregunta de Maciel Padilla, que es ¿cómo determinan qué animales o plantas pueden ayudar a innovar a la ingeniería geotécnica?
Sí, esa es muy buena pregunta. Porque ese es, yo creo que el reto más grande, uno de los retos más grandes. Y la verdad es que no sabemos. Al empezar, no sabemos. Podemos leer artículos, podemos hablar con colaboradores de biología, pero hasta que no se hace la investigación, no se puede definir qué tanto va a ayudar una nueva estrategia a la ingeniería geotécnica. Yo creo que la mayoría de los procesos que se han ayudado, que se han estudiado pueden ayudar. El de las serpientes yo creo que sí, lo hemos demostrado, lo de las raíces de los árboles también, pero yo creo que uno que tal vez sea más difícil de adaptarlo es el de los túneles de las hormigas. Y el problema es que hay una diferencia de escala muy grande. Las hormigas, voy a enseñar aquí la imagen que tenía. Aquí yo creo que si la pueden ver. Las hormigas, los túneles que ellas construyen son muy pequeños. Entonces usan el mecanismo de arching, del arco que se crea alrededor del túnel para que los túneles sigan siendo estables. Esto se me hace más difícil implementarlo en un túnel mucho mayor. Cuando la escala espacial se incrementa, el mecanismo del arching pues tiende a desaparecer o a reducirse. Entonces, yo creo que ese es un ejemplo que científicamente es muy, muy interesante, pero prácticamente creo que es un poco más difícil. Pero a final de cuentas, no es algo que se puede definir antes de hacer la investigación. Se tiene que pues, estudiar el proceso para después decidir si puede ayudar o no, o qué tanto puede ayudar.
Sí, ya veo, ingeniero. También hay una pregunta de un participante. Bueno, es preguntarle más que nada a usted ya. Si cuenta con bibliografía sobre fundaciones inspiradas en raíces de árboles. Y le agradece por compartir su conocimiento.
Sí, claro, claro. Tengo varios artículos que puedo compartir. No sé cuál sería la mejor manera. Si gustas, me puedes enviar un correo.
Sí, eso creo que sería la mejor forma. Le envío yo un correo y solicitándole esas bibliografías. Listo.
Ok, muy
Listo.
bien.
Tenemos una última pregunta sobre su presentación. ¿Qué le recomendaría a los estudiantes de ingeniería civil que deseen especializarse en un tópico tan vanguardista como los pilotos bioinspirados?
Sí, es buena pregunta. Pues mira, yo creo que lo principal es hacer algo, digamos, como seguir tu interés. Si alguien está interesado en un tema vanguardista, yo creo que eso es razón suficiente para enfocarse en eso. Y no tener miedo o no tener como desilusión pues sí hay un poco de escepticismo. Y yo creo que el escepticismo o como digamos la resistencia a cambiar o la resistencia a ideas muy nuevas es parte muy natural de lo que hacemos como ingenieros civiles. Es una parte muy, muy saludable. porque al construir una estructura, un edificio, un puente, pues tenemos una responsabilidad inmensa y si las cosas no salen bien, pues las consecuencias son muy grandes. Entonces, la resistencia al cambio es una cosa buena. Eso hace que el cambio sea lento. Entonces, se requiere paciencia, se requiere pues, dedicación, pero mi recomendación sería no confundir esa característica de nuestro campo, de que las consecuencias son muy grandes, con el hecho de que no se pueda mejorar nuestro campo. Nuestro campo se puede mejorar muchísimo. Va a ser un cambio lento, se tiene que demostrar que se puede mejorar y tenemos que adaptar tecnologías nuevas, tenemos que adaptar cosas como impresión a 3D, tenemos que adaptar inteligencia artificial, todas estas cosas. Y nos tenemos que adaptar y todo esto a largo plazo nos va a ayudar. Entonces, yo creo que al tener ese interés, al entender que el hecho de que el cambio sea lento no quiere decir que no debe de haber cambio. Esa es una distinción muy importante. Y yo creo que la tercera es mantenerse, digamos, informado de las nuevas tecnologías que van saliendo, que tal vez no aparenten tener mucho que ver con la ingeniería geotécnica, pero yo estoy seguro que en un par de años muchas de estas tecnologías o de estos nuevos campos nos pueden ayudar y nos pueden impactar de una manera importante. Entonces es mantenerse curioso, de aprender cosas nuevas, de implementar cosas nuevas.
Muchas gracias, ingeniero, por su recomendación y su punto de vista. Creo que a todos nos ha inspirado esa respuesta. Bueno, sin nada más que agregar, o sea, le agradezco que tenga su predisposición por compartir su conocimiento y le mandamos un fuerte abrazo por todo el capítulo estudiantil GeoUPC.
Bueno, muchas gracias. Ha sido un gusto y un honor y si cualquier participante está interesado puede enviarme un correo y podemos discutir. Y bueno, nada más agradecerles una vez más.